Good morning, everyone. Hold on, just take us off mute. Welcome to my presentation on spacecraft engineering for beginners. It's quite an exciting time in space at the moment. I don't know whether anybody was watching this morning, but there was actually a rocket launch from Kazakhstan taking some astronauts to the International Space Station. So if anyone was up at about 7:30 this morning, they would have seen that launch live. There's also a number of other things going on, which I'll talk through in the presentation, but hopefully by the end of it, you'll have an appreciation of what I do, what the world of space engineering is about, and hopefully one or two of you will be keen to get involved. So let's start with the beginning, the basics. So what is space and how do we get there? And then we'll go on to something that's more relevant to me, is how do you then be a spacecraft engineer? How do you build those things we send up into space? And then what's in the future? So when you eventually pursue a career in spacecraft engineering, what will the world look like? What will we be doing then? So what is space? Well, space is very unlike Earth. So where you're standing or sitting at the moment, you have air to breathe, you have nice green trees around you providing oxygen, you've got gravity holding you down. Now space is very different. So if you go about 100 kilometers straight up, which is less than the distance from driving from London to Birmingham, you'll suddenly find that there's no oxygen. You'll suddenly find you're in a very cold space environment. There's lots of radiation. It's generally not a nice place to be. So if you're an astronaut, you need protective suits, you need a spacecraft to get you up there. It's a very challenging environment to build for. So here we are, there's a view of the Earth's atmosphere taken from the International Space Station, just to give you an impression of how thin it actually is. If you had a standard globe in front of you, it would only be about a couple of millimeters off the height of that globe, that atmosphere. So it's very thin, but there is quite a lot of air there and it offers us a lot of protection. So on Earth, we don't need to wear spacesuits. That atmosphere above us protects us from all the harsh radiation and cold of space. Now, where are we in space? Well, if any of you stand out at the moment on a clear sky, you'll see a fair number of these up in the night sky at the moment. So we're on Earth. Now, tonight is actually quite an interesting astronomical event. So if you look roughly northeast, if you've got a clear sky, you'll see Mars as a bright red dot. From a spacecraft design point of view, that's quite useful. We can send spacecraft quite quickly to Mars when it gets close to us, as it's all the sun. And it becomes more difficult when it's right around the other side. If you look to the south and east, you'll also see Jupiter and Saturn in the night sky as well. And if any of you have, then you might even be able to make out Saturn's rings. So it's really interesting time to look up if you can avoid all the clouds and the rain that we're having where we. So how do we get into space? Well, there's lots of different ways and they're expanding all the time. When I was growing up, the main way of space was the Discovery space shuttle. And that was the exciting launch vehicle that we had when we were kids. We watched lots of launches of Discovery and the other three, I think, space shuttles. Now there's lots of launches coming into the market. So, like I said, if you were watching this morning, able to see the one on the middle left there, the Soyuz one launched this morning, taking 3 astronauts up to the International Space Station. So, an American lady and 2 Russian men. And then the one that I'm more used to dealing with is the one on the center right, the Ariane 5. So that's the one we use for the European launches. And that can deliver some quite big spacecraft up into space and on their way to other planets. And the Americans now are producing quite a range of launches. So the Falcon Heavy is on the right. And there's another test that's actually going on this week of another launch system called, I've written it down, I have to remember, Bezos. He's the guy that owns Amazon. He's looking to help the US Space Agency get, so that's part of the development for that. So again, test launches for that this week. So it really is quite an exciting time this week for space. How big are these launches that we're looking at? How much effort does it take to get something into space? Well, the Ariane launch, which is the one I'm familiar with, 55 meters tall. So that's a bit difficult to imagine, but if you imagine something like 4.5 buses end to end, that's the sort of thing you're looking at. And if you bear in mind most of that rocket is there to get the rest of the rocket into space. It's only the very top bit of it that will have the spacecraft in. So that's 750, a lot of aircraft, or 120 elephants, depending on your scales, is principally fuel. So we throw loads of fuel back of it to get the front end into space, and that's how we deliver our spacecraft up beyond the atmosphere. So how does the launcher work? Well, let's compare it to something you probably on holiday. If you take a camper van or a car, you'll have your guidance system on board, which will be your sat nav or your mum and dad's knowledge of the road that they're driving. You've got the fuel, which you'll fill up at a petrol station before you go. You'll have your payload. Now, that's probably you, plus a load of clothes that you want to take, plus anything that you want to keep you occupied when you're on your holiday mission, shall we say. And then you need a structure around you to protect you when you're driving. And that's exactly the same that we would have on a spacecraft going into space. You have your guidance system, which helps guide the rocket, keep it straight as it goes up in space, but then gently curve it over so we can get into an orbit. You need all the fuel to make it go. You need the payload. So instead of sending you on holiday, we'd be sending a spacecraft into space. And we need the structure to hold it all together, because that launcher, as it goes up, shakes a lot and it gets a lot of aerodynamic pressure on the front of it. There you go. That's typically what it would look like inside. And the thing that we're launching is only that little bit on top, but the rest of it's there to get it into space. So how do we get into space? Well, what's the physics? So some of you may have touched upon Newton's laws at school. This is exactly the same principle. Rockets work by throwing propellant, so fuel, out the back of it. And that action of throwing something out the back creates an equal and opposite reaction, which pushes you into space. But because Earth's gravity is so strong, and because we've got such a long way to climb to get out of the Earth's atmosphere, you need to throw quite a lot of material out the back of your rocket to get you up into space. Now, this is where a handy bit of physics comes into play about where you actually position your launch site. So if you ever have a look at any of the famous launch sites that we use around the world, so Kazakhstan for the Europeans, Florida for all of the American launches, French Guyana for the European Ariane launches, you'll find that they're all at the equator. Now, there's quite a convenient point about the physics of the Earth spinning, is that stuff spins. As you get closer to the edge of it, you feel a centrifugal force which pulls you outwards. If you stand in the middle of a roundabout as it spins, you won't feel any force throwing you out to the sides. If you stand on the edge, you will. Now, the same is true of the Earth. So if we stand on the edge of the Earth, or the equator in this point, as it spins, we get an extra boost. And that is quite useful in terms of throwing our rocket into space. We still need to use a lot of fuel and a lot of propellant to push our rocket, but the extra spin of the Earth as it goes round is a bit of a bonus. It helps. So that's why all of our launch sites around the world tend to be based around the equator, or as close to the equator as you can get in the country that's launching. So unfortunately, with the Zoom meeting, I can't show you the Ariane 5 launch, but instead I would point you to an even better launch, which is if you look up on NASA television this morning, you'll be able to find the launch of the Soyuz rocket that went up taking the astronauts to the space station. And you can easily find that on Google. So I'm sure with your teacher's help, you'll be able to look it up and see the launch. And that actually occurred this morning. So that's probably the most relevant example I can think of. So what do we send into space? Well, all sorts of things. There are literally thousands of satellites in space. It's getting quite crowded. So we have to be very careful now. Space, you think, as being a big place. But actually, the number of orbits up there that we put spacecraft into are quite constrained. Some of those spacecraft, if we're not careful, can hit debris, can hit bits of rockets from other spacecraft. So we have to be very careful about where we put those satellites these days to avoid that happening. But satellites are I guess the bread and butter of my work. So we launch satellites for all sorts of reasons, for satellite navigation, for telecommunications, for science, which is sort of my background. We also launch probes. So anybody that's ever taken an interest in Mars exploration will know that we've launched quite a few rovers to Mars to go and explore. And actually there's a European rover which we at Airbus in Stevenage have built and is being prepped for a launch to the Red Planet to go and look for life. So that's, again, an exciting time for us. And humans. So humans go up into space on the space station. And it's now possible that we can have humans in space for years at a time, which is an interesting experiment in itself. How space affects the human body is quite a complex science. So we say the word satellite, and I use this every day, the phrase satellite, but what does it actually mean? Well, there's two types of satellites. So we have natural satellites, which is just any object that's orbiting another object. So the moon is a natural satellite of the Earth, and the Earth in itself is a satellite of the sun. It just means that it's going around another object. We create artificial satellites, so we produce spacecraft that we send up into space. Now, to get into space, as I said, you've got to throw a lot of propellant to get yourself up out of the atmosphere. But then to get into orbit, it takes even more work. If you imagine that as you're going up into space, you've then got to start moving sideways to get around the planet. And the idea of an orbit is that eventually, if you throw yourself around the planet fast enough, you'll fall at the same rate as the Earth is dropping away from you. And if you do that, then you'll be in an orbit around the planet. You're basically dropping towards the planet at the same rate as the planet curves away from you while you're going around it. So you're just constantly falling. And that's what we term as an orbit. But to do that, you need to get very, very, very fast. So in this instance, we're talking something of the order of about 28,000 kilometers an hour. Now, to give you some perspective, a typical satellite going around would travel about 7 kilometers every second if you were to look at it going overhead. And if you get a clear night and you go to a really dark sky site, it's now possible to see satellites in orbit above us. You can see them as what look like white dots traveling across the night sky. And if you're very lucky, just after sunset and a clear sky in a dark area, you'll be able to see them traveling overhead. So satellites from my side, what does it take to build a spacecraft? Well, we need all sorts of things. You need a structure. You've got to hold it all together. While you go up on that launch vehicle, it's a very shaky environment. It bounces around as the rockets fire it up and it gets above the Earth's atmosphere. You need a structure then to hold the whole thing together. You need antennas. You've got to be able to talk to Earth and ground stations. People on the ground will have communications equipment, be able to tell the spacecraft what to do or receive communications from it. You need a payload. So in this case, it's what instruments we're going to put on board, what scientific things we're going to do, what computers and systems of measurement are we taking? Are we measuring sea surface temperature? Are we looking at pollutants in the atmosphere? Or are we just taking images to populate Google Maps? We need a thermal control system. So this is my area of expertise, radiators and MLI. So these are shiny foil blankets, the gold on the center of that picture that helps keep the spacecraft warm. But also we have equipment on board that tends to generate a lot of heat, and we've got to get rid of that heat into space. We need guidance systems. So in the same way that you need to use a sat-nav when you travel around on Earth, we need guidance systems in space to make sure our spacecraft stays where we put it. You need batteries to store all the electrical energy. So most spacecraft use the sun as a power source with solar arrays gathering that energy. And then we need batteries because occasionally those spacecraft will go into the shadow of the Earth away from the sun, which we call the eclipse. And then they need the power from the batteries to back them up. So, as I said, there's quite a range of applications for spacecraft that we design. So there's telecommunications. So anybody who watches Sky Television has a radar, has a satellite dish on the side of their house, will have it pointed at a satellite, which is in what we call a geostationary orbit. So it stays in the same place relative to the Earth. And you use that to pick up your Sky television signals. We have Earth observation satellite and spacecraft. So these are the ones that help predict weather and how the climate is changing. I worked on one a few years ago called Sentinel-5P, which I helped to launch. And that has been up now 3 years as of yesterday. So we had a bit of a celebration that it's still functioning. And that is still providing really useful data on pollutants in the Earth's atmosphere. And positioning. So when we were talking about going on holiday and using your sat-nav, well, that sat-nav, satellite navigation, it needs satellites in space to actually tell that sat-nav where it's positioned. So without those satellites, you wouldn't be able to use your sat-nav. Here's some examples of the spacecraft that we send up for telecommunication satellites. So our one that we've been producing at Stevenage in the UK for a long time now is the Eurostar platform. It's a very big spacecraft. It doesn't look it in that picture on the left, but that satellite is about the size of a Range Rover car, just the middle bit of it. And if you imagine whizzing over your head at about 7 kilometers a second, you can imagine the sort of engineering challenge we've got to get that into space. Now, we've launched, I think, in excess of 50 of those, and they're all still functioning perfectly. So that's a real achievement for the engineers who've been involved in that over the years. We're now working on what are called constellation satellites, so OneWeb, OneSat. So these are lots of smaller spacecraft that we launch in big clusters into space. So the idea is they're sort of cheap and cheerful. I choose cheap in a relative sense, but they give us the options of providing worldwide internet cover or satellite navigation. But instead of designing one really expensive one that we launch, we design lots of smaller, cheaper ones where we can live with some of them perhaps failing during their lifetime. So Earth observation. So this is where I tend to get more involved. We produce a lot of spacecraft for the European Space Agency. So we do all sorts of things to help the European Space Agency out with their Earth observation. So this is really key. At the moment, with the challenges that we face with global warming and climate change, it's really key for us to be able to observe from space how the climate is changing over time. So we're looking at ocean monitoring with the Sentinel programs, Sentinel-6, Pleiades, which is a cluster of spacecraft which take images, TerraSAR-X, which is using radar to map the Earth's surfaces, and the METOP programs to look at how the weather patterns are changing due to climate change. So with those sorts of satellites, we're able to get views like this, which 100 years ago would have never have been possible. We now can have really accurate pictures of what our planet looks like. And right down to the very small details. So again, 100 years ago, this would have been unthinkable, having aerial images like this, where you can now zoom into street level. So it's amazing how far we've come. Positioning. So anybody who uses a sat-nav at the moment will be familiar with the GPS, but Galileo is the one that the Europeans, up until quite recently, we were going to be involved in. We still are as Airbus as an entity, producing the European GPS, which is called Galileo. And it's actually going to be more accurate than the GPS system. So the sat-nav that you have in your car has a bit of an error associated with it. You could be within about 5 or 6 meters of where you actually are. With this Galileo system, I think it's of the order of about 1 meter resolution now, so it's far more accurate. Now, the really interesting stuff. So probes. So these give you 2 examples of the sorts of spacecraft at Airbus that we've launched to explore the solar system and space. So Solar Orbiter on the left, which is going to be a spacecraft which takes our closest ever looks at the sun. That was actually launched, I think, last year, and I've worked on this. And it's going inside Mercury's orbit around the sun. So it gets very, very close, and there's a big heat shield on the front to stop it getting too hot. And then as it goes around the sun, it's taking loads of photographs of it, and it's understanding all the physics about how the sun works. At the same time, we've also launched Bepi Colombo, which is going to Mercury, because Mercury is a very hot planet. It has one side that constantly faces the sun and gets very, very hot. And we want to understand a bit more about it, because at the same time as being one of the hottest planets, it's also got ice at the poles. So there's a lot of things we don't understand about Mercury, and very interesting to explore. So there's a view of sun from Solar Orbiter. The resolution actually now is getting much more fine, so we can take really close-up pictures and understand how all those patterns emerge on the sun due to the twisting magnetic field and the interaction with the heliosphere. And then we're also going out into the solar system. So that was going into the center of the solar system. Now we're looking at also options for going out. So to Mars, ExoMars. So that's the flagship program in the UK. So at Stevenage, we've been spending, I think, the last 10 years working on the design and development of this ExoMars rover, which will go to Mars and drill into the surface. And then when it's drilled in, it will extract cores of Earth, soil. It'll extract those and then be able to test them to see whether there are any microbes that exist within the soil that it's extracting from the surface. So it might finally be able to answer the question of whether there's even just primitive life on Mars, which is something that other rovers up until now haven't been able to do. ExoMars itself is an amazingly challenging program. We're used to building spacecraft that go into space, but in this program, we're having to design a spacecraft that takes a rover to Mars, deploys it onto the surface, and then allows the rover to drive around and drive between different locations. And that is quite a feat. The surface of Mars can get extremely cold, so electronics can start malfunctioning. You get dust storms, which can cover over solar panels and clog up equipment. You're also dealing with driving around with big boulders and things in the way, so it's a challenging navigation program as well. JUICE, so anybody who's knows anything about Jupiter will know that it's surrounded by a number of small moons, some of which we know already to have liquid oceans on them. So we think it's watery oceans underneath a frozen ice cap. Now, Europa, which is one of the most famous moons of Jupiter, has an ocean underneath its ice cap, which is bigger than all of the Earth's oceans combined. Now, the question arises, well, what's in that ocean? We'd love to know. So JUICE is going to explore that by traveling to the icy moons of Jupiter and having a look around and seeing what's there. And then, I think as part of that program, we're actually looking at providing some sort of device that will go through the surface eventually of one of the icy moons. We're not quite sure how to do that, but maybe melting our way through the ice caps is the way to do it. And then have a look for life there as well. So we're, I would say, at a very exciting point in space exploration, because we're now at the point where we're trying to explore other planets to see whether life exists elsewhere in our solar system and even beyond. Humans, by contrast, are a lot more delicate than spacecraft. So it's very difficult for us to get out and explore the solar system than you would think. So we go to the International Space Station now, but the International Space Station isn't that very far away from Earth, actually. It's only about 400 kilometers above, which is about driving to Birmingham and back again, shall we say, from London. So it's not that far. But even just that slight excursion outside the Earth's atmosphere means that we, as humans, are subject to an environment that we were never designed to be in. It gets extremely cold in space, about minus 270 degrees Celsius. So people would freeze. There's no pressure. So the moment you go outside the space station, if you don't have a spacesuit on, then your blood will boil on your skin. So you need something to keep you protected. There is huge amounts of radiation coming from the sun. Now, our planet has a magnetosphere around it, which protects us. Now, fortunately for the International Space Station, it's just inside that magnetosphere. So it gets some protection as well, but we still need a little bit of shielding. So there's a lot of aluminium around the outside of the spacecraft, the International Space Station, that offers a bit of protection to the astronauts as well. So fortunately, they're protected. But when we sent astronauts to the moon, they traveled outside of that magnetosphere. And actually, if you read any of the interviews with any of the people that landed on the moon, you'll note that when they were traveling there, they kept seeing flashes in their eyes. And those flashes weren't because they were seeing anything externally, it's because there were high energy particles that were traveling through their body and hitting the back of their retina and their eye, and making flashes that they could see. And it wasn't something that they were looking at, it was literally just a process happening inside the eye. And that's because of all this high energy radiation that was traveling through them. Now, going to the moon only took about 3 days, and then 3 days back again. So they weren't subject for those sorts of challenging environments for that long. But if we start to go off and explore the rest of the solar system, if we want to send astronauts to Mars, we're going to have to deal with all of the health implications for astronauts going there and back again, the intense radiation, the lack of gravity, and even the lack of daylight when you're in the space station, that lack of vitamin D that you would have on your skin, the feel-good chemicals. There's a whole science associated with humans in space. But again, it's a really interesting topic to get involved in. So that's the International Space Station. As it said, the clues in the name, it is really an international collaboration. So there's all sorts of parts provided by different space agencies. The European part is the Columbus module, which is the white cylinder bit in the bottom part, which is the science module for the European Space Agency. So they conduct a lot of experiments there into the effects of microgravity. So what happens to things when they're growing and they don't have gravity there. Now, if you've ever grown a house plant, or if you go outside and look at any plants, you know that they grow upwards, and they grow upwards because of a process called geotropism. They know which way's down, and basically they grow away from the gravity where the gravity is pulling them down. Now, if you grow a plant in space, it doesn't have gravity. So how does it grow, and how does it know which way is up and what happens? And all those sorts of physical effects are sort of interesting things to study, not only in plants, but more complex creatures as well. So the Columbus module addresses those sorts of questions and a whole raft of other questions as well, to do with how science actually behaves in an environment away from the one we know on Earth. So there you go. There's some examples of the sorts of experiments we do and what happens on the International Space Station. So perhaps one of the interesting ones, if you look at the top left, there's somebody doing some exercise there on the International Space Station. Now, you don't realize it, but when you're walking around on the planet, just the sheer act of you pushing up against gravity all the time keeps your body very healthy. You're constantly exercising your muscles. Your body is constantly replacing the calcium in your bones to keep your bones healthy and strong. Now, when you go to the International Space Station, you don't have any of that. You don't have any stress against your body. You're floating around in a vacuum. So if you're not careful, your muscles start to waste away. And another process happens, which is the calcium actually starts to leak out of your bones, and your bones start to decalcify and become weaker and weaker. So you need to do exercise. Now, the astronauts on the International Space Station, they have to do quite a lot of exercise just to replicate the environment we see on Earth. So something like 2 hours of exercise a day, and that's quite vigorous exercise. So that's lots of running and weightlifting and everything else, just to simulate what you do by getting up in the morning, walking around, going to school, coming home again. So it's really challenging, and we're going to have to address that if we send people to Mars. How do we keep that up? So also we do the extravehicular activities, so sending the astronauts outside the space station to repair and fix things. Again, that's quite a challenging process, can last hours, and you need the protective elements of a spacesuit to protect you from the harsh environment of space. And there's some of the scientific experiments we're looking at as well. So the growing plants in a vacuum, how do they behave? How do they grow? Also, how do things like liquids behave? So we used to, on the bottom right corner, we used to liquids when we pour them out of a glass, hitting the floor and creating a puddle. But in space, you don't have that gravity effect. What controls it is the surface tension and viscosity effect. So it forms bubbles, and that can be very interesting for spacecraft, because when we're designing spacecraft, we've got propellant in tanks, so fuel. If it bubbles inside the propellant tank and doesn't go where we need it to, it can cause big problems. So engineering on my level, engineering has to be a team effort. We often see pictures of individual astronauts or individual engineers performing a job, but engineering is by far and away a team effort. There's no one person that will ever have all the answers, but as I like to say here, everyone has a piece of the puzzle to help build a spacecraft. So you get lots of different roles. You get technical specialists, team leads, managers. And here's an example photo of one of the spacecraft we built, the Sentinel-5P one. I'm lurking at the back on the left. But this is just a small example of the team that was attending the tests just to get the spacecraft through one of the test campaigns that we went to. So if I had to say what are the key aspects of being an engineer, I would say that it's being a team person, working as a team. You obviously need to have a great deal of enthusiasm and passion for working in spacecraft and a good knowledge of it. But if you don't communicate and you don't have that enthusiasm, it's going to be difficult to put a spacecraft together, because you need to work with others. As an engineer as well, we're also torn in many directions. We work for a commercial company, so when we're producing spacecraft, we've got to be mindful of, sometimes there are launch windows that we need to get in to launch our spacecraft in time, because the planets are always moving. If we want to launch a mission to Mars, we've got to be acutely aware when Mars is closest to us so we can launch for them. So it's no use having the spacecraft being built 2 years later than it's needed if we can't then get it there. And things like quality come into play. When we're building a spacecraft, you've got to have a design that works. If you launch a 300 million euro spacecraft and there's any concerns that it's not going to work, it will never get approved for launch. So you've got to be really, really on the design of it. But the enthusiasm and passion, probably the easiest one to fulfill, because if you work on any space missions, then it's quite exciting stuff. So a bit about me then. We talked about what it is to launch spacecraft, what spacecraft are made of, where they go. What do you do if you want to become a spacecraft engineer? Well, there are lots of different routes, but let me give you an example of the one that I took. So many moons ago, I studied GCSEs at school and A-levels, and I took an interest in engineering and maths and physics at the time. So I studied maths and further maths at A-levels. And I would suggest if anybody wants to go into spacecraft or engineering at all, then maths is definitely one of the courses you need to be able to take, because there's a lot of interesting but hard maths involved in engineering. After I'd finished my A-levels, I was still interested in engineering. I didn't quite know exactly what field of engineering I wanted to go into, but aerospace sounded quite interesting. So everything to do with planes, but the space aspect as well was quite appealing. So I studied that at the University of Southampton and completed my master's degree in 2004. I then had quite an interesting opportunity come up as a graduate placement at Lockheed Martin, working on re-entry vehicles. So for a time, about 5 years, when I started my career, I was working with the US government developing re-entry vehicle technologies. So when we say re-entry vehicles, those are things that come in through the Earth's atmosphere. So when you're suddenly going from 17,000 miles an hour down to 0 as you come through the atmosphere, you generate a lot of heat. So you need protective coatings for all this, the re-entry vehicles that come back from the space station or come back from exploring the solar system. So, and that work took me on a lot of travel. So I ended up traveling to the US quite a lot. And there's a picture of me just on the right, a long time ago when I was actually visiting in the background a display of the Saturn V launch vehicle. So that's the one that took people to the moon in the 60s and 70s, just to give you an idea of how huge they are. And then after that, in 2009, I decided to change course a little bit. I'd done all the re-entry vehicle work, but I wanted to get really involved in the space aspects, so going outside the atmosphere. So I started work at Airbus in Stevenage as a thermal analyst. So a thermal analyst is somebody who analyzes using computer models all the spacecraft and builds up these computer models and really understands how the heat flows around the spacecraft. And then that eventually led me to the career I'm in at the moment, which is to be a thermal architect. So I'm responsible for designing all of the thermal control systems of the spacecraft that we work on. So that's how to keep the spacecraft at a nice stable temperature. Everything we design in terms of computers, in terms of rocket systems, they're all designed to roughly function around room temperature, about 20 degrees. So when we design spacecraft, we've got to keep them at that sort of temperature. So, and that's quite challenging when space can get very hot and very cold, depending on where you are. So we do lots of different things to help design those thermal control systems. As an architect, I now oversee the development of those thermal models to build up pictures of how the spacecraft behaves. So there's an example of what a thermal model looks like in the top right-hand corner. That's a computer-generated model of a spacecraft we were working on. And then once we've done that, when we build the spacecraft and we've put in all these thermal control systems, we then take the spacecraft on a test campaign. So we'll build the spacecraft and we'll take it to, there's only about 3 places in Europe you can test these spacecraft, because you need a very complex test environment. So if you see that picture at the bottom, that's a thermal test chamber. So what that does is it replicates space on ground. We can't get rid of the gravity, but we can get rid of the atmosphere. So that chamber pumps out all the atmosphere. So it's effectively in a vacuum. And we can get rid of the heat as well. So that chamber is also what we call cryogenically cooled. So they pump liquid liquid helium around the chamber. And that brings the temperature of the chamber down to well below minus 170 degrees Celsius. So that simulates the cold and evacuated space environment that spacecraft would go into. And then we run a whole series of tests and test the spacecraft works in all those colder temperatures. So you can imagine coordinating a test campaign like that amongst a big group of engineers is hard work, and it really puts the thermal engineer through his paces. So Airbus in the UK, so where we work in Stevenage, so we've already touched upon some of this, developing the Mars rover. So yeah, at the beginning, well, even at the beginning of this year, that photograph on the left shows the Mars rover being built in the clean rooms at Stevenage, so that you can see some very nervous engineers in the background looking through the glass as it's getting put together and lowered into its, I think, the transportation assembly so it can get sent for testing. That rover, if you look in the clean room at the around it, it's all covered in stainless steel. It all looks bright and shiny. And that's because when we send the rover to Mars, we don't want to take any life with us. Because if we take any bacteria or any life with us, when we look for life, we may have accidentally brought life with us, and we don't want to do that. So that clean room has to be absolutely sterile. So it's far cleaner than a surgical clean room. And all the people working on it have to wear special suits and everything else to stop contaminants getting on the spacecraft. So it's really challenging thing to build. And then give you some other examples of the things we work on as well. So we have our own Mars yard at Stevenage, where we have a big sand pit, where we drive the prototype Mars rovers about to simulate how the rover would drive on the actual surface of Mars. And we also build the other spacecraft components at Stevenage as well. So there's telecom satellites and mechanisms that we use in space are all built and assembled at Stevenage, and then often go off to Toulouse in France for the final spacecraft assembly. So yeah, an interesting place to have a look around. We talked about test. Testing a spacecraft, as I mentioned, is one of the most difficult aspects of my role. So when we get the spacecraft to test chambers and we're putting it in, often those tests will run for several weeks, and they run 24 hours a day. You can't pump down the chamber over 24 hours, get rid of all the air, and then recover it again because everyone wants to go home and have a sleep. You know, you put it into that configuration and then you run that test 24 hours a day. So we often work on shifts when we're away on test. So I will go in and I will start, say, a day shift that starts at 12 in the afternoon and runs till 12 midnight, and then a fellow engineer will take over and run the night shift, and then we swap again at the following 12 hours. So it can be really challenging for doing that for 2 weeks, a bit of sleep deprivation. But the satellite safety is always the prime objective. So we do all this testing, but we want to make sure we look after the satellite so it never gets damaged. I'm the top pink circle in this diagram, but just to give you an idea of the other people that are involved in spacecraft design, because it's not just thermal engineers, there's all sorts. There's propulsion engineers who design all the rocket systems, there's mechanisms engineers who design all the complex mechanisms for deploying things like solar arrays. There's AOCS, which is attitude and orbit control system engineers, so they make sure the spacecraft points in the right direction. AI, which is assembly, integration, and test engineers, so they're the people that are responsible for building it. So there's a whole raft of different careers, different team members that go into building a spacecraft. So it really does take all sorts. My current project, so this is one I'm working on literally 5 minutes before I joined this presentation, is biomass. So biomass is to look at how much carbon is locked up in the atmosphere around the world. Now, this is really quite crucial to understanding how much carbon is going into the atmosphere, because we really don't have an understanding of how much carbon goes into the air and then gets sucked up by trees. Well, biomass is going to be launched in 2022, and we'll look at that by using a big radar to measure how much mass of trees there are as it goes over things like the Amazon or the equatorial rainforests. And by using this, we'll build up the clearest picture we've ever had of how much deforestation is going on and how much carbon is being locked up in newly planted forests. So it really is quite a useful bit of information to fill in the picture. So what's in the future? Well, we'll touch on this briefly. So constellations are going to be a big part of the future. So if any one of you becomes a spacecraft engineer, I would imagine you'll end up in some part being involved in constellations. It's the way forward. Lots of small spacecraft providing coverage around the world for things like internet and for GPS. Return to the moon. So Literally yesterday, the UK signed into what's called a memorandum of understanding with the European Space Agency to start providing bits of the spacecraft and bits of the infrastructure that will take humans back to the moon. So it's going to be principally an American-led activity, but the service module, the bit that provides all the power and all the bits that help the spacecraft work to get to the moon, will be built by the Europeans. And I work with some people now who are involved in the development of that. So we could well be back to the moon within the next 10 years, which is going to be very exciting. And travel to Mars. And today, I said it was a very exciting time in space this week. Today, we've actually signed at Airbus a contract for returning samples from Mars. So the idea is we send a rover to Mars, we dig up some samples, and we shall bring them back on an Earth return orbiter, which is the spacecraft that we're going to build at Airbus. So the idea is dig up some samples of soil, launch them back into space from Mars, collect them with another complicated spacecraft, bring it back to Earth safely through the Earth's atmosphere, and we'll be able to analyze them on Earth, which is a really exciting prospect, but immensely challenging. If you can imagine all the aspects of that space program, it's going to be very, very complicated to do. Right, I think that concludes me talking. So I'm going to stop there and hopefully take some questions. So what I would suggest is if you've got a nominated person in your group and you want to use the chat function to send me a question, then I can try and answer them.
Hi Glenn, it's Julianne. We've had a couple of questions. Thank you for that. That was a great presentation. We've got one from Vanessa, and it's about old satellites. So are they brought back down to Earth once we don't need them anymore, or they stop working?
That's a very good question. Yeah, old satellites really do cause a bit of a problem. If you can imagine, for the last 30, 40 years, we've been launching lots and lots of satellites, hundreds, into space. And when we first started launching them, we really didn't care. When they reached the end of their mission lifetime, we just left them where they were, because the view at the time was, well, space is really, really big, so it doesn't really matter what happens to them. Now that's become a bit of an issue because everybody has adopted that approach, and now space is full of old leftover junk spacecraft. So now when we design missions, we're having to basically design them so that we either bring them back into the atmosphere at the end of their lifetime, so that they're not a big piece of junk traveling around that might hit another spacecraft, or we put them into what's called a graveyard orbit. So we make sure we've got enough fuel left on board the spacecraft, so we move it out to an orbit where no other spacecraft are, so we don't hit anything else. But yeah, it's a really challenging topic, because although we can do that for the spacecraft we design now, all the spacecraft that have been launched in the past are all whizzing around, potentially hitting each other and creating lots of junk and more debris. And we need to be really careful about that. And at Airbus, we're actually designing a system that will go up and try and retrieve old spacecraft and bring them back down to Earth with a harpoon system. So it sounds a bit crude, but it's probably one of the best ways to do it, to gather up old spacecraft and bring them back into the atmosphere, or at least park them in an orbit where they won't cause damage.
Yeah, that's really good, because there's another question on there from somebody that says, how do satellites avoid being hit by space junk?
So well, yeah, it's a really, again, a really hot topic. So another good question. The International Space Station actually has to perform maneuvers to avoid bits of space debris. So if you ever keep an eye out for the International Space Station in the news, occasionally what you find is they actually do what's called an orbit control maneuver. So they move into a slightly different orbit to avoid a bit of space junk coming the other way, and then they'll move back again. Occasionally, they'll get hit by tiny bits of space debris, and it can cause damage to things. And we've had spacecraft in the past that have been hit by bits of debris and have caused damage to the solar arrays. Usually we try to design spacecraft so that if they're hit by small bits of debris, they're usually okay. And when I say small, I mean even a fleck of paint in space, traveling at the speeds it does, 7 kilometers a second, if that hits another spacecraft traveling the other way at 7 kilometers a second, that's a lot of kinetic energy. So yeah, it's a really big problem, and one that spacecraft engineers in my time and in the future will have to deal with. So yeah, good question.
Yeah, we've got a couple more. One from Giovanni. Would a manned space station orbiting Mars be possible, seeing as it has no magnetosphere? atmosphere? Sorry.
Yeah, well, that's a good question. Yeah, when we go to Mars, we're going to have to work out a way to shield humans from all the radiation as we travel there, and also when we get into orbit around Mars. So one of the most intriguing prospects, there's a lot of ways of doing this that people have tried to suggest. So one is that, well, astronauts, when they go to Mars, they're going to need to take a lot of drinking water with them because they won't have access to any, and they need it for the 3 years that they're going to be traveling there and back again. So one option is you literally surround the spacecraft with all of the drinking water, and the drinking water will actually act as a bit of a shield to the radiation. So we could do that. Another option is, believe it or not, this is actually a credible solution, is that we actually use the people's poo. So when they've been to the toilet on board the spacecraft, they can actually pack that into bags and use it as part of the shielding around the spacecraft to protect them from the radiation. So it's a bit grim, but yeah, that's a possible solution.
It works.
If it works, it works.
Absolutely, absolutely. One final question we've got on there at the moment. If anybody does have any further questions, and we do have a little bit of time left, so just pop them in the chat, that would be great. Can materials be reused after a spacecraft is no longer used?
Yeah, good question. It's very difficult to get spacecraft back again. That's the problem. When we launch something into space, we give it a lot of speed to get up there, and we don't often think about bringing it back down. When something comes through the atmosphere, we have to slow it down. And the typical way of slowing it back down again is to use the air as a brake. So we come back through the atmosphere and we compress against the air as we come back. So that's what re-entry vehicles do as they come back bringing astronauts. And that generates hugely extreme temperatures, so well in excess of 2000 degrees Celsius. Now, if we have a spacecraft that didn't have any protection on it and it came through the atmosphere, pretty much none of it would survive. There's only little bits of it that might survive as they come through the atmosphere. So we would either need to develop a way of repurposing spacecraft that are in space to give them other jobs, which is something we're looking at. So what we call sort of modular spacecraft, which we redesign in space to do different jobs from what they were originally designed for. Or we try and bring it back to Earth in a controlled fashion where it doesn't burn up, which is what we used to do with the space shuttle. So the space shuttle would come back and land. They would replace bits of it, but most of it was still intact and could be reused again. Yeah, good question.
Yeah, thank you for that. So yeah, if anybody has got any further questions, that would be great. If not, thank you for joining us today. There is a survey that if you could, hopefully Vanessa will put that in the chat shortly. And if you could fill that out, that would be fantastic. We have another question quickly. To what extent do you get involved in designing new materials?
New materials. Well, yeah, space is one of those. It's an interesting view on new materials. A lot of our customers don't like us developing new technologies because there's always a risk with anything new. It's untested. But yes, we have to design new technologies occasionally because things change and new technologies come out, new materials. So when I used to be a re-entry vehicle engineer, we were constantly developing new sorts of materials and trying out new technologies. I remember at one time we were actually developing a re-entry heat shield that would push gas out of the surface of it. And it was inspired actually by kitchen worktops. Kitchen worktops come with a melamine surface on them. And melamine outgasses, so it generates gas. And that's quite good when you've got a re-entry heat shield. You generate that gas coming out the front of the heat shield, and it actually acts as a bit of a barrier, pushing away the hot air in front of it. So we were looking at new technologies inspired by existing physics. So yeah, there's a lot of people out there working on new materials, new technologies, and those will go into new spacecraft in the future. But we have to balance that between the risk-averse nature of our customer who wants to reuse stuff that they know works. So it's always a fine line to tread. But yeah, good question.
Brilliant. Thanks for that, Glenn. Thank you, everybody, for joining us today. Thank you, Glenn, for delivering that presentation. It was really, really good. This presentation will be available on our website next week. So keep an eye out, but I'm sure we'll be sending through the link to everybody. Lovely. Thank you very much, all.
Okay, thank you.